Hello, my name is Sevin Kwon, and today I will be discussing my paper, A Simulation and Comparison of Propulsion Systems for a Manned Mission to Mars. The planet Mars has never been explored by man directly, but it has been explored in numerous unmanned missions. For example, the first was Mariner 4, which was a spacecraft that did a flyby of Mars in 1964. Then, in 1975, the Viking 1 and 2 landers were the first spacecraft to land on the surface of Mars. And since 1997, multiple rovers, the first of them being Sojourner, have explored the surface. Now, one reason why many people want to send man to Mars is because since Mars is the most similar planet to Earth, it is best for human colonization. Now, one of the benefits of human colonization is that it will preserve mankind in case of a global disaster. For example, if an asteroid were to hit Earth and wipe out all life on the surface, then the people on the Mars colony would survive and continue the human race. However, before any of this is attempted, before the spacecraft is sent to send the colonists to Mars, it is first necessary to determine which exact propulsion system will take the colonists there. So the exact question this paper shall attempt to answer is, how would different space propulsion systems compare in performance, specifically in travel time and propellant consumption, in a near-future manned-Mars mission? We shall attempt to explore this question by conducting a series of Python program simulations of Mars missions. The spacecraft that this program series will simulate is the SpaceX Starship. This is a heavy lift craft which, according to one paper, has a dry mass of 130 metric tons, a payload capacity of 90 metric tons, and a propellant capacity of 1,200 metric tons. Its default propulsion system is 6 Raptor chemical rocket engines, but in many variations of our hypothetical simulated Mars mission, these will be replaced by other modes of propulsion. So the way that these simulations are to work is that the spacecraft Earth and Mars are all plotted upon a 2D coordinate plane, as you see here, with Sun being at the origin. The spacecraft will start at the same position as Earth, and it will orbit the Sun in the same direction as Earth. That is, counterclockwise. All of these objects, the Earth, the Sun, and Mars, will have the coordinates subjected to solar gravity, in which case it is simulated by Newton's law of universal gravitation, as you see here with the AX and the AY and so on. For the propellant expenditures of the spacecraft, we'll use the rocket equation, as you see here. As for the spacecraft's velocity, the starting velocity will be dependent on how much delta V its propulsion system produces at the departing burn. Its velocity throughout the transfer, if it only has a high thrust engine, then the solar gravity will be the only thing affecting it. But if it also has a low thrust engine, the low thrust engine will produce constant acceleration throughout the transfer. For these simulations of the orbits, we will assume that the orbits are circular and coplanar for simplicity, even though in real life it is clearly not the case. So the spacecraft is said to have arrived at Mars when the radius from the Sun is 228 million kilometers. That is the semi-major axis of Mars. When this point is reached, Mars is plotted in reverse, starting from the spacecraft's end position until it reaches for the same time it took for the spacecraft to reach Mars. And then, once that time has elapsed, it will stop, and this end position of Mars will be the actual start position of Mars if this were a real mission. Of the 6 propulsion systems that these programs will simulate, 3 of them are high thrust, meaning that they produce kilonewtons or meganewtons of thrust. The first of them is the traditional chemical rocket, which involves a fuel and an oxidizer reacting to produce thrust. This is the kind that is used on most interplanetary missions and launch vehicles as well. Then there's the nuclear thermal rocket, which involves a nuclear reactor heating a working fluid or propellant, liquid propellant, vaporizing it into very hot gas and expelling it as exhaust to produce thrust. This engine has never been used in space, however, it has been built and extensively tested on the ground. Then there is the nuclear pulse engine, which involves the spacecraft being pushed from behind by nuclear bombs exploding. This spacecraft design, for obvious reasons, has never been built in its full form, has never been tested in its full form or in space or on the ground, but the operating principle has been simulated using non-nuclear models. The other three propulsion systems are low thrust systems, which means they produce millinewtons or newtons of thrust. First among them is the solar sail, which is a very large, very thin sail being pushed from behind by solar radiation pressure, and this pulls the spacecraft behind it. And this propulsion system has been tested in space as early as 2010 with the Icarus mission of the Japanese Space Agency. Then there is the ion thruster, in which the propellant atoms are ionized by removing electrons from them and accelerated out through electrically charged grids. This system is very commonplace in commercial satellites, which use them to keep the satellites in orbit. Then finally, there is the magnetoplasma dynamic, or MPD thruster, which ionizes propellant into plasma and accelerates it out using magnetic fields. This system is more experimental, but it has also been tested in space as early as 1995, in fact. So in the simulations, the acceleration caused by these systems, for the ion thruster and the MPD thruster, it is in the tangent direction to the orbit of the spacecraft around the sun. But in the case of the solar sail, the acceleration is simulated as being outward from the sun, perpendicular to the tangent of the orbit. And since these systems are not strong enough in thrust to take a spacecraft out of orbit, they have high thrust booster engines. For the solar sail, it is a chemical engine to get the spacecraft in and out of orbit. For the other two, it is a nuclear thermal engine. So, there are three main trajectories that the spacecraft can take on these missions. First of them is the Hohmann transfer, in which the spacecraft enters an elliptical orbit around the sun with the periapsis at the tangent to the Earth's orbit, and the apoapsis tangent to Mars' orbit, on opposite sides of each other from the sun. These are used by the aforementioned high thrust engines, the chemical, the nuclear thermal, and the nuclear pulse, and the delta V's and the transfer time are governed by the equations written to the side. There is also another option for a high thrust engine to consume the maximum amount of propellant possible to depart at the maximum possible velocity, while still keeping enough propellant to enter the orbit of Mars. This produces a minimum amount of time, but expends a maximum amount of propellant. A third way, with the low thrust engine, is to depart at the same departing velocity as the Hohmann transfer using the high thrust booster engine, and then continuously during the transfer accelerate using the low thrust engine, and then fire the booster engine again to enter Mars orbit. This is used by the solar sail with the chemical booster, the ion engine with the nuclear thermal booster, and the MPD with the nuclear thermal booster. So here you see the table of the values of the results obtained from the computer simulations. For each of these criteria, each of these rows, the best value, depending on the criterion, is marked green, and the worst value is marked as red. If any propulsion systems have the same extreme value, only one of them is marked. For the delta V's, for the departing and low thrust delta V's, the higher is better because that means the higher the velocity of the craft. For the arriving delta V, however, the lower the better because that means the lower the propellant expenditure for that burn. From the simulations, we find for the high thrust engines that the minimum transfer times being the transfer times obtained by expending the maximum amount of propellant for the maximum speed. In this, the nuclear pulse engine produces a shorter trip time than the nuclear thermal rocket, which in turn produces a smaller trip time than the chemical rocket. We also find that the minimum propellant expenditures, being the propellant expenditures of the Hohmann transfer, in this, the nuclear pulse engine, again, has a lower consumption than the nuclear thermal rocket, which in turn has a lower consumption than the chemical rocket. In this case, since the nuclear pulse engine outranks the nuclear thermal rocket and the chemical rocket in that order, in both criteria, it can therefore be said that the nuclear pulse engine has a higher performance overall than the nuclear thermal rocket, which in turn has a higher performance than the chemical rocket. For the low thrust engines, we find that the transfer times rank in the following order. The MPD has the shortest time, followed by the ion thruster, and then the solar sail has the longest time. For the propellant expenditures, and this is including the high thrust boosters, the ion thruster system has the lowest expenditure. The solar sail has the next. That is, the boosters have that much propellant expenditure, and then the MPD thruster produces the highest expenditure. However, as we see, there is no clear relationship between the rankings of these two criteria, so it is difficult to quantify the performance overall. So another way we can is that we take the amount of transfer time decreased by the low thrust engine compared to the corresponding Hohmann transfer, and we divide that by the amount of propellant increased by the same system, and we take this time to mass ratio. The greater the ratio, the higher the performance, because the higher bang for the buck, so to speak. And we take this ratio and we find that the MPD thruster has the lowest ratio, followed by the solar sail, and then the ion thruster, meaning the ion thruster has the highest performance overall. Now, that is all for today's presentation. Does anyone have any questions? Alright then, thank you very much for listening.